All right, let's take a look at Chapter 8. Chapter 8 introduces us to index models. And what we're going to find is this concept of index models is really going to save us some time. It's going to make our the task of creating portfolios with multiple assets. It's going to make it more workable. I'll show you how. Let me remind you that the standard deviation of a portfolio looks like this. For a two-asset portfolio, WA squared sigma A squared plus WB squared sigma B squared plus 2 WA WB covariance of A and B. All right. So that's the standard deviation of a two-asset portfolio. If you remember, we see this is asset A's contribution to the risk of the portfolio. This is asset B's, left off a exponent there. This is asset B's contribution to the risk of the portfolio, unique contribution. And this then is the interactive risk, because we take into account how each asset is varying relative to each other, their covariance. Again, that was two assets. Let's see what it looks like with three assets. The standard deviation of a three-asset portfolio. WA squared sigma A squared. WB squared sigma B squared. WC squared sigma C squared. Plus 2 WA WB covariance AB plus 2 WA/WC covariance AC plus 2 times WB/WC covariance BC. That's the standard deviation of the three-asset portfolio. Okay. Again, same concept. We're seeing, okay, this is A's individual or unique contribution to the risk of the portfolio. This is what B is contributing individually. This is what C is contributing. And then we have to take into account the covariance. How do these assets vary relative to each other? So we've got all these different measures of interactive risk between each and every asset. So again, that was just 3. Look how long our formula is getting. What if we had 10? Well, now we're going to have even more. I mean, this would be a huge formula. So ultimately, we still have to take into account covariances. I mean, there's not going to be a shortcut there. If we have 3 assets, we're still going to take into account the covariance between each of those, each asset relative to the others. But in terms of calculating covariance, we're gonna find out there's an easier way for us to calculate the covariance between each of these assets, and that's what we're going to do with our index model, right? So instead of, and by the way, let me just show you something real quick. Let's say we had our spreadsheet out, and I'm going to put asset A right here and asset B. And here's the return for asset A for period 1, for period 2. Let's say we get 30 returns. So the return for 30 periods. I do the same thing for asset B. So I've got all those different returns through 30 periods. Well, I can calculate the covariance. In Excel, I can highlight the first column and I can highlight the second one. I mean, it's a formula, or it's a function within Excel where I would highlight this column and highlight this column, and boom, it's going to give me the covariance. All right. Now remember, what's really happening here, the covariance of asset A and asset B is equal to the standard deviation of A times the standard deviation of B times the correlation between those assets. Okay, but my function in Excel will knock it out for me pretty quickly. But if I've got 3 assets, I need to do the same thing now for asset C. And so I would need to put another function in and say, okay, now highlight column A and column C, and now give me the covariance between A and C. And then I would also need to do another step if I needed to know the covariance of asset B and asset C. I highlight one column, I highlight the other column, and I get the covariance. So that's a lot of steps. You know, if I had 10 assets, I'm going to have actually 10 times 9, which is 90. You divide that by 2. Just as here we have 3 different assets, 3 times 2 is equal to 6. Divide that by 2, we've got 3 unique covariances. Okay, we've got AB, AC, and BC. If we had 4, then we've got 4 times 3, which is 12. 12 divided by 2, which is 6 individual or unique covariances. If we had 10 assets, we've got 45 individual covariances. I think you can see that's going to be a lot of Excel work where we have to keep doing this. If we had 10 assets, we had to have to calculate, because we need 45 covariances. But there has to be an easier way for us to get that. And there is, okay? And so what we're going to do in this chapter is, instead of looking at how every asset varies relative to each other, we're going to see how does each asset vary relative to the same index, the same benchmark. And we can still calculate the covariance. We're going to easily be able to calculate the covariance between each one of these assets. It's going to be a lot easier. Again, we don't have to look at how each asset is really varying relative to every other asset during this time period. We're just going to look and see how does every asset vary relative to the same index. Okay? And then it's going to make our life a lot easier. All right. So to begin with, I'm kind of march through some of the relevant parts of this chapter and kind of help develop some things. First, I'm going to write this statement: the rate of return on a security can be decomposed into sums of its expected return or expected and unexpected components. So your textbook writes that this way: the expected rate, or the rate of return on a stock I, equals, well, what we expect it to be plus what we don't expect it to be, or what we're surprised. Right? This is the expected return. This is the unexpected return. So what does that mean? Well, you know what? We may have a pretty good handle on what we think the return is going to be on Walmart next period, or Nike, or Home Depot. Okay? And so we've got a pretty good expectation of what the return's likely to be. Well, that's this first component. But something may happen this next month, or this next week, or today, that's going to impact the return on Walmart. Some new information, something that was not expected. So ultimately, then, the rate of return that we earn is equal to what we expected plus the reaction, or our response to something that was unexpected. Well, next your book says, okay, well, suppose then a common factor, and we're going to call that common factor M. A common factor M is a macroeconomic variable that affects all firms. That's probably true, don't you think? there's a macroeconomic variable. Let's call it the market. Okay? You know, the markets, when the market moves, most stocks tend to move. You remember that the Dow Jones Industrial Average is only 30 stocks. And yet, when the Dow's up, most stocks tend to be up. So let's rewrite this, or at least your textbook rewrites this to say, okay, well, if that's the case, then the return on a stock I equals what we expect it to be plus when the market moves, right? Some unanticipated macro surprise. Plus, again, something that is unrelated to the market, but it's a firm-specific surprise. That makes sense to me. I hope it does to you. All right. So maybe next period we're expecting something from Nike. Okay. And so we have an expectation of what we think that return is going to be. A couple of things might change what the actual return is. Maybe the market tanks. Maybe the market increases. Maybe there's some kind of inflation, unemployment, interest rate change that's going to affect the markets. So that would be captured in the M variable, that there was a macroeconomic surprise that was unexpected that impacted our stock. In addition, there could be, again, still some firm-specific surprise. Nike introduced a new tennis shoe, or Nike got some good press or some bad press. So what we're saying then is that the return equals what we expect it to be plus any surprises. Systematic, which is, I'll put that down here, this is really a systematic influence, and unsystematic. So then your textbook says, so with this in mind, the variance of our return, which is a measure of risk, right? The variance of R sub I comes from two unrelated sources. The systematic and the unsystematic. Those are unrelated. There's no correlation at all. One is market, one was a firm-specific surprise. So we can write then that the variance, which is sigma, if you remember, so the variance of our returns is equal to the variance of the macroeconomic variable plus the variance of this firm-specific surprise. Now, I think your book does a decent job of marching us through this. It's kind of hard to follow all the paragraphs, so that's why I'm trying to do this for you. Okay? Well, then they go on to say, okay, well, if we all agree with that, then let's also agree that some firms are more sensitive than others to the macroeconomic surprises. I agree with that. There are some firms that are a lot more sensitive when interest rates change, or unemployment, or inflation. Okay? So we're going to add another variable. We're going to add some kind of coefficient to our model, and it's going to be beta, which is a sensitivity coefficient. For firm I. So beta sub I, beta subscript I, is a sensitivity coefficient for firm I, for company I. It tells us how sensitive company I's returns are to market movements. And so now we can rewrite then the variance for the firm, it's equal to the beta for the asset squared times the variance of that market surprise plus the variance of the firm specific surprise. Okay. Well, what we find, and it's going to make our job quite simple, well, not quite simple, but more simple, less difficult, is that if we do this for all of the assets, so that's the standard deviation for asset I, but we could get the standard deviation for asset J, K, L, M, N, O, P, right? All different assets. The covariance between securities let's say I and J is equal to the covariance of asset I with asset J is, since we already have a measure called beta which measures how asset I moves relative to the market, and we've got to measure, well, okay, during that same time period, how did J move relative to the market? That's how we can calculate our covariance. We actually don't have to look at how I is moving relative to J individually. We can look at how I moves relative to the market. Okay, well, how did J move relative to the market? I know this is a silly comparison, but how about this? How about if two people ran a 100-yard dash? One person ran it in 10 seconds. The other one ran it in 11 seconds. Same distance, okay? We don't have to put them head to head to see which one ran faster. They ran against the same index, didn't they? And so maybe it's a lousy comparison, but we're able to gauge something about their relative performance by comparing their performance, their individual performances against the same index. We don't have to find everybody and say, okay, let's have one big race to see who's the fastest. We know who's the fastest. Like I said, probably that one just popped into my head. I didn't think about that one before I tossed it out there. So it may make sense, it may not make sense. I liked it though. All right, so let's remind ourselves then what we can see, or actually what we already know, is total risk equals systematic risk plus unsystematic risk. We know that. Well, let's rewrite what we had up here, this formula. The total risk of a portfolio, or rather of a security, the total risk, sigma I squared, equals the systematic risk. So here's the systematic component. Beta I squared sigma M squared, that's the systematic part. And here is the unsystematic part. Boom. So let's start writing down some of the things that are going to help us. Covariance. And I'll repeat that formula up there. So the covariance, just so you know, is going to equal the product of the betas times the market index risk. So the covariance of asset I and J equals beta I times beta J times the risk of the market, sigma squared M. If we want to know the correlation between two assets, the correlation between asset I and J. So the correlation of asset I and asset J is equal to the product of the correlations. So the product of the individual correlations with the market index. In other words, if I want to know the correlation of asset I and asset J, I'm going to take the correlation of asset I with the market and multiply that times the correlation of asset J with the market. Okay, I'm going to come over here to the right here and remind you, you've seen this before. The covariance of asset I and asset J is equal to the standard deviation of asset I times the standard deviation of J times the correlation between I and J. Solving for correlation, I could write the correlation IJ equals covariance divided by the product of their standard deviations. Okay. I tell you that because, let's come over here, I'm going to calculate or show you the layout for the correlation, to calculate the correlation between asset I and J. So starting with, I'm going to start with the correlation I with the market. Okay, so look at your formula here. If you want to know the correlation between two assets, I and J, you take the covariance between those. So if I want to know the correlation between asset I and the market, I take the covariance of asset I with the market, and I divide it by, as you see over here, the standard deviation of I times the standard deviation of the market. Well, we just established above what covariance is. So the covariance of asset I with the market, we're going to take the beta of asset I times the beta of the market. I'm up here, you know, looking above up here where covariance is, times the variance of the market. Okay, that's covariance in the numerator. In the denominator, I need the product again of their standard deviations. So standard deviation I times the standard deviation of the market. Remember that the beta of the market is 1, isn't it? And so right there where I've got a beta of the market, that's a 1. So this can simplify then to beta of asset I times the variance of the market divided by sigma I sigma m. Again, because the beta of the market is equal to 1. Alright, let's do the same thing. The correlation between asset J and the market will equal the covariance of J with the market over sigma J sigma m. Beta J, beta market, variance of the market, sigma J sigma m. Again, because the beta of the market is 1, we can write beta J sigma squared m over sigma J sigma m. So to calculate then the correlation, change colors one more time. So if I want to know the correlation between asset I and asset J, we said above, it's the product of those correlations. So I'm going to take the correlation of asset I with the market times the correlation of asset J with the market. And so this one and this one. That's all I'm doing. Beta I sigma squared m over sigma I sigma m times beta j sigma squared m over sigma I sigma m. What your textbook gives you is this, the final formula, beta I times the variance of the market times beta j times the variance of the market divided by sigma I sigma m sigma j sigma m. Seems like a big formula, doesn't it? I don't know why they don't simplify it a little bit. I'm going to go ahead and simplify it just a little bit because we've got some sigma m's. I've got sigma m squared in the denominator. So I'm going to rewrite this to be beta I times beta j times the variance of the market divided by sigma I sigma j. So that's how we can calculate correlation between two assets. You don't have to derive the formula, but right now you could see if I wanted to know the correlation between ExxonMobil and Procter & Gamble, I don't have to get the returns for each one of those assets over time, put it in a spreadsheet, and calculate the correlation or covariance using an Excel function. All I need would be the beta of each asset. I need the standard deviation of the market, and I need the standard deviation of each asset. And I can plug it into this formula. Okay. So this is all part of this concept called the single index model. We're using a single index, maybe it's the return on the S&P 500, to see how everything varies relative to that one index. Therefore, it keeps us from having to calculate how much each asset specifically varies relative to each other. So I'm going to write this down, the single index model. All asset returns are explained by the same index. For instance, maybe the S&P 500. Okay. Now, as we develop this, we saw this in our last class. The capital R represents excess returns. So capital RI is equal to the return on the asset minus the risk-free rate. So that's excess returns. Big RM is the excess return in the market. So it would be the return on the S&P minus the risk-free rate. And so if we regress, if we estimate a regression, and let's say we get, let's say for Hewlett-Packard, okay, we get the returns on Hewlett-Packard over several months, maybe 36 months, and the return on the S&P during the same time, I'm sorry, the return on a T-bill, and the return on the S&P during the same time period, and we calculate the excess returns. Then I can regress my excess returns on my company stock on the excess returns of the market. Let me go to a new page here. Just make sure you understood what I just said. Here's month 1, 2, 3, 4, all the way through, let's say, month 36. I get the returns for Hewlett-Packard. So there's the return for Hewlett-Packard for period 1, for period 2, for period 3, month 3, all the way through month 36. Okay, I'm going to get the returns on the S&P during the same time period. So the return on the market for month 1, for month 2, through month 36. I also need to know some kind of rate of return, a T-bill rate. So I'll get the risk-free rate for month 1, for month 2, through month 36. Okay, so I've got all that. Now what I'm going to do is create another column over here. This will be my excess returns for Hewlett-Packard. So this is going to be, if this is column 1 and that's column 2 and this is column 3, then my excess returns are going to be column 1 minus column 3. So basically, you know, well, you can see if I take this first return here and I subtract what the risk-free rate was, and that gives me all the way down. I'm also going to get R sub m. This is simply going to be column 2 minus column 3. So I'm getting my excess returns all the way down. And so then I can estimate a regression where this column is going to be my dependent variable and this column is going to be my independent variable. You can easily do this in Excel. Independent. Anyway, in Excel, when you click on a function, it says regression. You know, you'll click on regress or regression. It's going to ask you for the array or the column of numbers, which is the independent and which is the dependent. And our dependent variable, our regression equation, is going to take this form right here. R sub I at time period t, we're going to regress. That's what this is. Once we estimate that regression, we'll get an intercept. That's the intercept of our regression, plus beta I times the excess return plus this term. It's an error term, but it represents the firm specific surprise. Okay. So this is our, it says expected excess return. This is our beta, which is our measure of how sensitive our returns are to market volatility. So it's the sensitivity to market volatility. And then this last term right there is our firm specific surprise. And the expected value, by the way, of that is 0. I mean, we don't expect there to be a surprise, because if we expected it, it wouldn't be a surprise, would it? Okay, so that just, if there is something that happens that is was not expected, it's going to impact the rate of return we earn. Okay, and we'll be able to identify it, because the rest of this is what we're able to predict. And so if we did have some kind of firm specific surprise, it would be reflected in that error term. Okay, so your textbook gives a couple of examples here. One, in fact several examples, and there's some in the back of the chapter. But one of the concept checks said, okay, why don't you assume that a regression produces the following. So it looks like there were 2 regressions that were done. And so the excess return of asset A then is defined in that regression. The output is 1% plus 0.9 times RM plus this, plus the firm specific. Let's see, where am I looking here? I'm trying to find where this is. It's on page 262, right? And Asset B's returns were also regressed against the benchmark, and it produced these regression results. We're also given the following, that the standard deviation of the market is 20%. The standard deviation of the surprise for firm A is 30%, and the standard deviation for the surprise for firm B is 10%. And the question is, find the standard deviation for each stock and the covariance between them. All right. So we start with what we know here. Let's see here, I'll move it to right there. All right. So we remember, if we go back and look at, we need this formula right to start with, right here. We know the total risk of an asset equals its systematic component plus its unsystematic component. And so we're going to say, okay, the total risk then of asset A equals the systematic component, which was if you go back and look at the formula, but we're going to take the beta for asset A squared times the variance of the market plus the variance of the firm specific risk. Well, from our regression we see the beta is 0.9, so that's going to be 0.9 squared. We're told that the standard deviation of the market is 20, so that's going to be 20 squared. We're also told that the standard deviation of the firm specific risk is 30%, so that's going to be 30 squared. So I've got 0.9, 0.9, 20 times, 20 times, and I'm going to add that to 30 squared. This gives me 1224. So the variance is 1224. The standard deviation of the variance is 34.99. So right at 35%. So the standard deviation of asset A is 35%. Let's look at the standard deviation of asset B. We'll do the same thing. Standard deviation of asset B. We take the beta for asset B squared times the variance of the market plus the variance of the firm specific risk for asset B. The beta for asset B is 1.1. So 1.1 squared times the variance of the market plus the variance of the firm's specific risk, which is 10% squared. And so if we multiply that, we're going to get 1.1 squared times 20 squared plus 100. I get 584. And if we take the square root of 584, I get 24.17. So we have calculated the standard deviation for asset A and the standard deviation for asset B. The next question says calculate the covariance between them. The covariance between A and B, well, Well, guess what? We've got a nice formula, don't we? We actually don't have to look at all the returns for A relative to B. All we have to do is say, well, we know how A moved relative to the S&P, and we know how B moved relative to the S&P, and we know the variance of the S&P. So we've got 0.9 times 1.1 times 20 squared, because 20 was the I think it was the standard deviation of the market, so we need the variance. So we've got 400, 1.1 times 0.9 times, I get 396. Right? I'm going to do one more concept check. Similar. This is concept check number 1 on page 261 that I'm going to do. So let me create the chart for you in case you don't have your book handy. We're given the following. Let's see, this is going to be the stock, dollars, beta, mean excess return, and standard deviation. So we've got stock A, stock B, stock C. We've got $3,000 invested in stock A. We've got $19.40 in asset B and $13.60 in asset C. The beta is 1, 0.2, and 1.7. 10%, 2 and 17, and 40%, 30 and 50. The question number 1, question A, says, what is the mean excess return for the portfolio? Well, the return of a portfolio is a weighted average. So let's see how much money total we have in our portfolio. We've got 3,000, we've got 1940, we've got 1360. Add all that together, we have 6,300. 6,300. Okay, so we need to calculate the weighted average. So we'll look at stock A first. Stock A, $3,000 of money, but so it represents 3,000 of our 6,300, and that has a return of 10. Plus asset B, 1940 divided by 6,300, so that's the percentage of it in our portfolio, times 2, plus our last one is 1360 divided by 6,300, and that's going to give us times 17. And so if we multiply all that out, you should get 9.05. So 9.05% is the mean excess return for the portfolio. Question B. They're asking for the covariance between asset A and asset B. Okay. That's easy because we've got this great formula. Remember, the covariance of asset A and asset B is equal to the beta of A times the beta of B times the variance of the market. So we've got beta of 1 times the beta of asset B, which is 0.2, times oh, I left off something. They gave us also that the standard deviation of the market index, this is given, is equal to 25%. So I need to multiply that times the variance, so it's going to be 0.25 squared. So 1 times 0.2, 0.25, 0.25, 0.0125. C. What's the covariance between stock B and the index, which would be the market index? Well, we do the same thing. What's the beta of B times the beta of the market times the variance of the market? The beta of B is 0.2. The beta of the market is 1. We're going to get the exact same thing, aren't we? Because we can see that the beta for asset A happens to be 1, which is exactly the same thing that the beta of the market is. So we get 0.0125. I'll come over here to D. Question D then says, break down the variance of stock B into systematic and unsystematic components. Alright, that's fine. We can do that. Here's what we know. We remember that the standard deviation, or rather the variance of asset B, is equal to its systematic components, which is going to be the beta for asset B squared, times the variance of the market, plus the variance of the unsystematic risk for asset B. This formula that I just wrote down right here, we've used it multiple times. It's right here. Well, that's not it. Let's see. It's right here. See? Total risk equals systematic and unsystematic. So we're given the standard deviation of asset B. It's 30%. It's 0.3. So 0.3 squared equals the beta for asset B, which is 0.2 squared, times the variance of the market, 0.25 squared, plus this. So 0.3 times 0.3, this is going to give us 0.09. 0.2 squared times 0.25 squared gives us 0.0025. So now we can solve for the remaining component. If our total risk is 9%, our systematic risk is 0.0025, then our unsystematic risk must be 0.09 minus 0.0025, which gives us 0.0875. So of a total risk of 9%, systematic risk is just a little bit of it. It's only 0.0025. Most of the risk is unsystematic. Most of the risk is the unsystematic risk, which is 8.75%. So this is again, this concept of single index is pretty powerful. You may not see it, and you may not fully appreciate it, but it is pretty powerful. Even though we still need to look at covariances between assets, even if we had, 6 assets, 6 times 5 is 30, divided by 2, that would give us 15 individual covariances. I know that's a lot to consider, but it's so much easier to get those 15 covariances using the single index model than it is to regress the returns for all those securities against each other, if that makes sense, to come up with those covariants. It's much easier to see how each one of these assets moves relative to the S&P, and then be able to draw the same conclusions by looking at that variation as opposed to each individual asset. All right, so I'm going to stop here. That's mostly what I'm going to want you to know from Chapter 8. We use that, though, this concept of a single index model now, into the last chapter that we're going to have before the test, which is the capital asset pricing model. So now that we can all agree, maybe in a sense, that it's important to look at one index, now what we're going to come up with is, okay, how do we price each security then? If we know that we can look at each individual asset and how it moves relative to some index, now we can try to price the risk. We can say, okay, since this stock tends to move more than the index, you should or tends to be more volatile than the index, then it's probably riskier and you should get a higher rate of return. If another asset is less volatile than the S&P, then it's less risky, and so maybe you would require a lower rate of return. So that's where we're going to go in Chapter 9, is we're going to use this important concept of an index, of a benchmark, one portfolio, one index that we can evaluate each asset relative to the same index and see if we can price the risk of those assets. That's called the capital asset pricing model, and it's coming up in Chapter 9. Okay, that's it. Bye.